The next type of response is our undamped response. So I've copied our total response here, and so as we see, it just continues to oscillate about the final value without getting any closer or any further away over time. And so let's look at an example transfer function that has an undamped response. So g of s is equal to 9 divided by s squared plus 9. So again, all we've done is we've kept that same general form we had previously, and we've just changed the parameters. In this case, we've made our a value 0. So like before, we can find our two poles. So we have 9 in the numerator, and our poles are now s plus j3 times s minus j3. So we have two purely imaginary poles. So two imaginary poles. So this is what corresponds to an undamped response. And so like with all the other cases, we can see what this looks like in our s-plane. So we have our real axis and our imaginary axis. And in this case, we're looking at plus j3 and minus j3. So we have a pole at each of those two locations. And so what we're going to talk about in a later unit is stability. And just sort of as a preview to that, if these poles were to shift more to the right, our system would become unstable. And so instead of having an oscillation that looks like this, we would get something that begins to grow without bound. Now, of course, eventually something in the system is going to limit that, or something in the system is going to break, but theoretically it would just continue to increase without bound. On the other hand, if we were to take this in the other direction, so if we were to move these poles to the left, what we would have is an underdamped system. So in that case, we would have this initial oscillation, but it would start getting closer, and so the frequency should still line up there, but it would start getting closer to the final value, and eventually it would become essentially the same as the final value given enough time. So those are sort of the two cases of how shifting the poles could change the response from this undamped case. But if we have the two poles perfectly on that imaginary axis, we have undamped response. Now for our natural response, so shown above is the total response. For our natural response, we have an undamped sinusoid with a radian frequency equal to the frequency of those poles. So undamped sinusoid with a radian frequency equal to imaginary part of poles. So in this case, that would be a radio frequency of 3. And so what that looks like is our natural part of C of t would be a times cosine of omega 1 times t, so that omega 1 in this case would be 3. A and phi here are just going to be constants based on other factors in our system.